Hello, everyone. We are Akanksha.
Dictionary.
Parker.
Yeah, for the past few weeks, we have been exploring how to implement Microsoft's new BitNet LLM attention kernel in hardware through leading HLS tools, including Vivado HLS, Allo, and Catapult HLS.
So what is the problem? Large language models typically utilize large bit width weights, which lead to substantially increased model complexity, energy consumption, training, and more importantly, inference time. Although we desire to fit such LLMs on smaller and smaller devices, the inherent complexity of LLMs makes it very difficult to achieve this goal. Enter BitNet, Microsoft's framework for a 1.58-bit LLM with ternary weights of values -1, 0, and 1. By substantially reducing the bit width of the weights in this way, the size of the model can be greatly reduced, leading to impressive speedups as well as real energy savings. So far, the model is only available in standard C++ executable form, running on specific architectures for general-purpose CPUs. Such a compact model with aggressive quantization provides opportunities to be implemented and optimized on hardware.
Based on this, we want to explore how such a model can be implemented in hardware using Vivado HLS and Allo for FPGA development, as well as Catapult HLS for ASIC development. By analyzing the trade-offs between accuracy, area, and performance of such implementation, we can evaluate the feasibility of deploying such models in real-world use cases. For our experiments, we use AMD Zynq 7000 SoC ZC702 for FPGA and design compilers NAND gate 45 nanometer for ASIC design.
All right, so let's start with Vivado HLS. So first of all, the source code is directly from Microsoft's BitNet GitHub repository. It's optimized for specific architectures such as x86 and ARM with heavy dependencies on other libraries such as Llama, so it's not directly amenable to RTL hardware translation. So luckily, work has already been underway by a fellow Cornell student, Kaixin Yang, who has translated the model into a generic, self-contained C++ implementation with clear distinction between layers for seamless mapping to RTL modules. The first task is changing all the dynamically allocated arrays to static size arrays, since the former is not compatible with HLS. This required significant reverse engineering to decode the sizes of each intermediate data structure being passed between layers in the kernel. Next, floating point data types are converted to fixed point data types using the APFix library. Floating point data types are not desirable for HLS due to the extra complexity for handling such moving decimal points. Multiplication division operations are also needed to be completely removed or modified to shifting operations to reduce the reliance on DSPs. Finally, standard C library functions like square root and exponential needed to be inlined into simpler logic or exchanged for modules provided by HLS math. For square root and exponential in particular, we experimented with approximations, but found that they produced relatively inaccurate results for this application, so we used the HLS math modules instead. So once the basic HLS compatible version was created, our attention can now turn to optimizing the kernel. Particularly the linear feedforward module incurred the most latency by far, so we needed to dedicate most of our resources here. In the original code, weights were packed in the second dimension of the input array in a sequential manner, requiring the innermost loop to have a complex array bound that was not constant. So to fix this, the input array was remapped to 3 dimensions so that the packing could occur in the third dimension, and the innermost loop of the layer could have a constant bound, so we could fully unroll it. The second loop dimension was also tiled for more fine-grained control over unrolling, which allowed us to achieve the best possible parallelism right up to the resource cap. So due to the small size of our FPGA, there were a lot of opportunities for parallelism that were left untouched. So evaluation on a larger FPGA would be left for future research. So our experimental setup, we've created 2 programs to interact with the attention layer. One sends and reads inputs via direct C simulation, while the other reads and writes the hardware FIFOs for the hardware synthesized model. So since the full-size model was unable to fit on the FPGA due to VRAM constraints, we evaluated quarter-size, 16th, and 1/64th size models on the FPGA to draw conclusions about the full-size model's performance. So to obtain our reference outputs, we've isolated the attention layer in Kaixin's source code such that we can send it specific inputs and read the outputs to get our desired values. So for execution time and latency, first we evaluate the execution time of the model in the FPGA as seen running in the video demo for the quarter-size model. Again, we can't synthesize the full-size model, so we record the execution times for the smaller models and apply a linear fit to project it to the full-size model. We also compare these times to those from the reference model obtained via C simulation, which we can get the full-size model's execution time. We see the smaller models perform better with the original model, but we would expect the hardware implementation to achieve a nearly 2x better performance were it to actually fit on the FPGA. The validity of the best fit line may be questioned since the reference model doesn't follow a perfect linear fit, but the synthesized latencies of each model does actually follow a linear trend, so we would expect that the predicted execution time for the full-size model is relatively accurate. So comparing the latency and resource usage of the optimized and unoptimized full-size model, there aren't really any surprises here. Latency improved by nearly 120x, but DSP flip-flop and LUT usage increased by 300 to 400%. We also apply a heuristic area score as seen to estimate the relative area impact of each design. This calculation is only meant as like a comparison point, of which we see like a 300% increase for the optimized design. So finally, we can look at the accuracy of our bit width choice. So the chosen bit width of the fixed point data type has a major impact on the overall accuracy of the model. Here we can see how the overall RMSE of the output values for a full-size model is dependent on the total and integer bit widths of the AP fixed data type. So larger integer bit widths, specifically around 20, provide the best accuracy, while moderate integer widths around 16 have the worst. So interestingly, the smaller bit widths tested around 12 are better than those with 16. This is likely due to rounding or truncation issues when the bit width is 16. Also interesting is the fact that RMSE does not change appreciably with total bit width for a fixed integer bit width, indicating that the integer bit width is more important for the intermediate calculations between layers compared to the fixed point bit width.
Yeah, so let's talk about Allo now. So what is Allo and why are we using it? Vivado and Catapult HLS are both industry standard tools. Allo, on the other hand, contrasts them by being open source from academia, which highlights its transparency and accessibility for research. Allo is a Python embedded accelerator design language. This means writing Allo implementations is very Python-like, so it's extremely intuitive to learn. One major difference with Python, though, is that it has a typing system. Allo has a lot of great features, making it easier to develop and export designs. Verification can happen at every way of the implementation, and it's very simple without requiring an additional test bench file. There are a wide range of optimizations, just like those in Vivado, such as pipelining, partitioning, and reshaping. And Allo automatically generates a Vivado implementation and a host.cpp backend to be ready to be run on the board. So what needs to be done to convert code to Allo-compatible code? First and obviously, we need to convert Kaijin's code, which is written in CPP, to Python. Then, similar to Vivado, Allo does not support dynamically allocated arrays. These need to be converted to static size arrays. We also need to convert all the C types to Allo types, which is shown in the picture below. And then, in order for Allo to call other kernels within the kernel itself, other kernels need to be void types and update arrays in place. So we have to update the code so that all the intermediate functions are void type. And again, like the example of that is in the picture below. And finally, just like Parker mentioned, we need to convert all the standard lib functions to be Allo compatible, just like Vivado. So when optimizing, resource cap was a huge limiting factor. Even before any optimizations were conducted, over 50% of LUTs were already being used. Therefore, of all the subkernels within the attention layer, we decided to optimize the linear feed-forward layer as it incurred the most latency. To optimize this layer, the float32 inputs were mapped to fixed type. And just like Parker mentioned in his slide, the quantized inputs were mapped to 3 dimensions in order to avoid complex indexing. And finally, we also use loop tiling in Allo over the second dimension in order to have more control over unrolling, rather than resorting to unrolling the entirety of the K0 loop. Here is a quick pie chart to show the latency distribution of the unoptimized design. Clearly, the linear forward layer causes the most latency, which is why we decided to optimize it. Here I have 3 designs. No optimization is a baseline design. Optimized with area limit is our final Allo design, where area restrictions are obeyed. And aggressive optimization aggressively loop tiles the linear forward layer by a factor of 24, rather than 2 in the area limited design. Looking at latency, the area limited design reduces to 1.3 million cycles from 26.5 million cycles, which is about a 20x speed up. The aggressive design is only at 500,000 cycles with about a 2x speed up compared with the area limited design. And if we look at the LUT usage of these designs, it is clear that the aggressive optimization design exceeds the allocated LUT usage by a lot, by about 40%. And the area limited design utilizes 99% of the LUTs. So we really believe that we optimize this to the best of our ability since we have no more LUTs left. Let's revisit the pie charts from before. So on the left, we have the pie chart for the area limited design, and on the right, we have the pie chart for the aggressive design. In both charts, it is clear that the linear forward layer takes up a smaller portion of the chart compared to the original one. On the left, we achieve a 19.3x speed up, and on the right, we achieve a 47.4x speed up. And if you look at the right, you can see that the aggressive design does a really good job to the point where the linear forward layer is no longer the bottleneck for execution time.
Moving on to the Catapult implementation. So why Catapult? Catapult is another powerful tool that stands out in the design and optimization of complex systems, especially for both FPGA and ASIC design flows. One of the key reasons for choosing Catapult is its strong support for System C and C++. And by using Catapult, we can efficiently meet the timing, area, and power goals, which are critical metrics in modern hardware design. The tool also provides us with a unique ability to explore trade-offs early in the design process, ensuring that performance and resource usage are tightly coupled. Catapult generates the RTL code that can further be imported to like FPGA or ASIC, and it can be further optimized, tested, and finally implemented. Well, we had to transition the code from Vivado HLS to Catapult HLS. There was a lot of things that we had to make compatible. First, for the data type, we had to use the AC int and the AC fixed libraries. And for the communication to the FPGA, we used the AC channel. For the math functions, most of the time we could work with AC math and C math, except for the square root and the exponential functions. For this, we used approximation algorithms such as Newton's method and Taylor's series expansion. We also experimented a lot on like the fixed width and like also trying to conduct more experiments to see which is the perfect precision that we would need, and also to avoid like overflow errors.
We tested the design for an FPGA specifically for the attention layer using the data that was quarter of the original size. Initially, the direct implementation of the algorithm made compatible with Catapult overutilized FPGA resources, with LUT users reaching approximately 106%. Upon analyzing the report, we identified that constant arrays such as weights were unnecessarily being mapped to LUTs. Leveraging Catapult's features, we remapped these constant arrays to utilize BRAMs instead. This optimization significantly reduced the area utilization, decreasing it by 4 times. For a fair comparison with Vivado, HLS, and Allo, we applied similar optimization strategies. During the scheduling task, we encountered high runtime in the linear feed-forward section, particularly in the inner loop tree. To address this, we implemented loop pipelining, which improved the runtime performance. Additionally, due to the way multidimensional arrays are represented in Catapult, we choose not to perform array partitions. These optimizations collectively achieved a latency reduction of approximately 4 times in FPGA, as you can see the results. Following the FPGA design, we use Catapults to target ASIC implementation. The tool successfully generated RTL, and the following graphs illustrates the comparison between our unoptimized and optimized results in terms of area latency for the ASIC flow.
All right, so now let's go over holistic evaluation and conclusion. So each tool has its unique design philosophy and workflows. Vivado is really tightly integrated with the Xilinx ecosystem, and it emphasizes the ease of use with many different FPGA designs. It focuses on leveraging Xilinx-specific optimizations for research, resource, power, etc. Allo, on the other hand, prioritizes rapid design exploration, making it simple to implement designs in Python, and even simpler to conduct verification. Automatic backend code generation also makes it incredibly easy to simulate and run on FPGAs. Catapult HLS uses advanced design abstraction capabilities and optimization frameworks, which instead caters to both FPGA as well as ASIC design spaces. So while all aim to convert high-level code into efficient hardware descriptions, their distinct feature sets and target ecosystems lead to very different design trade-offs and workflows, as you've seen throughout the presentation. So if you want to have a closer look at our project, you can visit our open source repository at this link. Finally, these are our references. So thank you for listening.